it swaps on its own sometimes. How about now?
Yeah, this is perfect.
Okay. Okay. Excellent. So so let me start. So just as a background, as Gutta said, I don't actually work in this field anymore. So this is mostly from my postdoctoral days back in 2003 to 2007. So I actually work on laser-driven accelerators now. So so my memory is fairly old. If you have detailed questions, I would direct them to Vandana, who is actually on the call. So it's actually useful to have her joining the call as well. So the field is actually fairly complex in some ways. It's a combination of quantum mechanics, optics, a little bit of electronics, and then mathematics. So I've tried to keep it at a BSc plus level. Some bits may be too low for you. Some bit may be a bit more complex. So we can, on an average, it should be, I would think, okay. So I mean, I left the title as a brief history of time intervals, which is essentially the journey to get to attosecond pulses. So I don't know how popular Big Bang theory is in India, but I'm hoping that most of you would have seen it, or at least have heard about it. So this is essentially one episode from this sitcom called Big Bang Theory, and it's basically a story of a bunch of physicists in California Institute of Technology, and what's happening there in their lives. So they are attending a physics ball at Caltech, and basically the president is asking a lot of questions. So one question, interestingly, was what is the shortest time period or pulse generated in the lab? And I think this was done a few years ago, around 2008, 2010, around that time. So at that time, I think the pulse was around 120 attosecond long. That was the shortest pulse that was generated. It is not the shortest anymore. So it kind of shows the evolution of the field. But it's interesting that the field of generating short intervals has actually even appeared in popular sitcoms like this. So as you know, this year's Nobel Prize was actually awarded for work in this field for three people majorly: Peri Agostini, Ferenc Krauss, and Lullier. So I've highlighted the three things from the Nobel citation. So this is exclusively for developing the experimental methods to produce attosecond pulses and enabling, essentially capturing or the study of dynamics, really fast dynamics that is happening in this time scale. So the reason I kind of highlighted those three things is that the field is actually much more vast, much wider, and a lot more people have actually contributed to it. And without their contribution, even the experimental methods or experimental developments wouldn't have been possible. And the reason I highlighted the word dynamics is essentially this is the entire theme of the talk, and this is primarily why people are interested in generating shorter and shorter time intervals. So this was this year announced in the first week of October. But if you look last year, there was another announcement of a similar prize called Wolf's Prize. And Wolf's Prize is actually considered one of the top prizes in physics. It's considered, the stepping stone to Nobel prize in some sense. But there, if you look at the two laureates are the same, Anne Lullier and Ferenc. They both appear as laureates here, but one person is different, and that person is Paul Corkum. So I basically worked with him during my postdoc. So he was my postdoc advisor in Canada. So the reason this Nobel Prize was in some ways surprising to us, or quite a few of us in the field, was because Paul is actually known as one of the godfathers of attosecond science, and because of the contributions that he has made. In fact, it'll become clearer as we go through the talk that the insights that he provided in understanding how some of the fundamental processes, especially there's a process called high harmonic generation, which I'll come to towards the middle/end of the talk. So without that insight, without what Paul provided back in 1993, the whole field may not have evolved the same way. So the impact of his work has been enormous. That single paper is a single author PRL, Physical Review Letters. It's got over, well, nearly 9,000 citations, and every year it gets at least a few hundred citations, and it's actually one of the most cited papers in this field, actually. So I just want to acknowledge Paul's contributions to this field. So Nobel Prize is not really everything. So anyone who works in this field actually knows Paul. So looking at talking about dynamics, talking about timescales, it's always good to put things in perspective. So again, going back to the title song of Big Bang Theory, it'll tell you in the title itself that the universe was formed 13 billion years ago, which if you convert to seconds, is over 10 to the 17 seconds. That's huge timescale. The entire universe, everything in it, including galaxies, stars, planets, all of them actually formed in billions of years of time scale. And then things that we look at, if you look at this scale, you should see that this actually it's not a linear scale. Yeah. So this is actually logarithmic. Otherwise, we wouldn't be able to see pretty much anything in this scale. So the man appeared over 30,000 years ago. That's kind of another time scale. Heartbeats once every second, roughly. Bees, they flap their wings in milliseconds. Nowadays, fast cameras are available that operate at a few milliseconds to a few microseconds. Electronics, fast electronics, especially integrated circuits, they work at nanosecond timescales. Chemistry, essentially, molecule motion, vibrations, bond happening, all those things happen essentially in femtosecond timescales. In fact, there was a Nobel Prize awarded in 1999 for using femtosecond lasers. I'll come to that in a second, to understand chemical dynamics. But if you go down further, if you go into the atomic scale, things that happen inside atoms, specifically motions of electrons, especially core electrons, the inner shell electrons, they happen in attosecond time scale. So to really understand the fundamental mechanics of nature, it's in a way you can say that you need to actually understand attosecond science. So this essentially is the story of dynamics across a period. So if you wind the clock back, roughly 100, maybe 120 years ago, the kind of dynamics that they were looking at was actually quite mundane. So they were, the kind of questions they were asking was, the horses were, motor cars were not available. So horses were really the fastest conveyance mode. So they were wondering, how horses run when they gallop. Do they always have one leg on the floor, or do they actually lift all four legs off the floor? So this, interestingly, was an interesting question. And if you look at some of the paintings that were done in the 18th century, maybe early 19th century, you'll see that they all had got it wrong. So most of the paintings would have one leg of the horse on the floor. They never really understood that horses can in fact lift all four legs until there's a guy called Edward Muybridge. So he's kind of seen as the father of motion pictures or movies. So he came up with this technique where he could actually click pictures very fast with a fast shutter speed camera. And you could actually freeze motion of horses. So you can actually see that there is an instant where the horse has all four legs off the floor, right? So this kind of settled the debate entirely. So I don't think people redrew the paintings, but I think at least since then, all the paintings were at least scientifically accurate. So before that time, we don't need to worry. But then this passion to understand really fast motions actually carried through. Cameras became faster and faster in some ways. So people started looking at much faster motions. So this is, for example, looking at the motion of a bullet through a balloon. You can actually see it's basically a balloon filled with water, just firing a bullet through it. You can actually capture the motion. You can freeze it in time. And some of these things were actually enabled by the invention of flash. So I'll tell you what the importance of flash is after a couple of slides. But essentially, the way to capture really fast motions depend on in cameras called a fast shutter. So the shutter speed essentially defines how good your freezing of the motion is, how good the blur is, for example. So if you use if you want to capture a really fast motion, maybe Usain Bolt running 100 meters in Olympics, or much faster events, things like hummingbird fluttering. If you use a normal camera, chances are that you wouldn't actually capture it properly. You see a blur, huge blur, because you don't really have the time resolution to capture the motion within that short time period. But if you use a fast shutter speed camera, which is what makes this kind of cameras very expensive, you can actually capture, you can freeze that motion in time. So this is okay based on mechanical motions. Shutter essentially says it's a mechanical motion. You can get shutters that operate at microsecond time scales. But if you really want to go beyond that, for example, this was supposed to be a movie, but for some reason, my laptop is Mac, but the computer that I'm using is Windows, so it doesn't really work. So imagine that these electrons are flying around. Okay, so I just have to talk through it. So essentially, if you want to look at electron motion, something like that, they happen in much faster time scale. So for example, you can calculate the natural time scale of an electron in a hydrogen atom. You can essentially assume the Coulombic binding potential of the electron. From there, you get the potential energy of electron, and you may not have studied this in bachelor's, but you may have come across this in master's. It's something called virial theorem, which kind of equates potential energy to kinetic energy in a closed system. This is partly why, for example, stars shine in some ways. So it's the same principle. So from there, you can actually get the velocity of the electron in the hydrogen atom, and then assuming the Bohr radius of the atom, you can actually calculate what's the time scale for its revolution. And it turns out the orbital period for an 1s electron in a hydrogen atom is about 150 attoseconds. So this is really fast motion. So obviously you can't use anything that is mechanical, or even things that are assumed considered faster, things like fast electronics and things like that. You cannot use this to directly capture really fast motions like this. So the question is, what do you do? So in a conventional camera, as we saw, you have a continuous illumination, typically natural light, or artificial lights, when you go to studios and things like this. But they are essentially continuous. The light is there all the time, and the things that you use to look at fast motions is the fast shutter. You move it very fast. That's the one that you physically move, to capture the fast motion. But as I said, you can't use this to capture much faster motions. So can you do something else? Can you, instead of moving something fast, actually can you not shine light continuously? Can you, for example, come up with a flash, and this is the invention of flash cameras, started in early, mid 1900s, so around 1940s, 1950s, flash cameras became popular. The idea was that although you have this ambient light, you shine a lot of light in a small time period, and the light basically goes and scatters from the atoms of the object. It comes onto your eye, or to the film in this case. But once the light is gone, it's essentially dark, or it's not as bright, and so you can actually illuminate fast motions that way. But again, typically flashlights are there for milliseconds or so. You can't really get to attosecond timescales. But the question is, can you create much shorter flashes? Can you create much shorter light pulses? So I will start using not flash, but from pulse from now on. So in order to understand how to create light pulses like this, it's important to understand, first of all, what light is. So this, I assume, you all know. I don't need to go through this. You would have heard this or learned this in your late +2 second year, I would have thought. If not, certainly in your bachelor's. You know that light, essentially, all light that we see is essentially an electromagnetic wave with orthogonal electric and magnetic fields that actually they're mutually orthogonal to the direction of propagation. So it's essentially a wave, and presumably you also know the mathematical way of interpreting a wave. So you write it as e power I omega t, which you can write as a cosine term, cos omega t plus I sin omega t. So we probably will need this later on, but if you don't know this, just take it from me that you can actually write this as a function of frequency and time. So basically, it's a time varying electric and magnetic fields. That's all you need to understand. But again, in the early 20th century, people, this was done by Maxwell, right? The whole field of electromagnetic theory was done late 19th century by Maxwell, James Clerk Maxwell. But came early 20th century, there were some phenomena that people couldn't really explain completely based on electromagnetic theory, things like black-body radiation. I'm not really going into the onset of quantum mechanics, but things that we want to understand here is that light has a dual nature. So they also have a particle nature. It's based on photons. Without that, you won't be able to, for example, explain things like photoelectric effect, where just by shining more and more light, you don't get more current. Only by changing the wavelength or the photon energy, you start seeing the current appears. Although, interestingly, Einstein never really believed in quantum mechanics. He had to actually adopt that to explain photoelectric effect, for which he got Nobel Prize. So the entire visual electronics that we see and take for granted, things like CCDs, video cameras, even TVs nowadays, entirely based on this phenomenon. So just as a background. So with this background, you can actually start thinking about a new type of laser. Essentially, if you look at from a quantum mechanical perspective, any light, no matter where it comes from some sort of transition, either from an atom or from a continuum transition. We don't need to worry about that, but consider atoms for a second, where I say, again, it's a very simplistic picture of atoms, where you have specified energy levels. So this again was the product of quantum mechanics, that there are specified energy levels that electrons can occupy. They can't occupy any energy state in between, but only certain states. And when electrons get excited by anything, either by light or thermal or electrically, they can go to they can absorb that energy and go to higher energy state. And when they de-excite, when they come down to the ground state, which normally all physical systems would like to do, they emit that extra energy, typically as photons. And this is how most of the light that we see nowadays, even the light bulbs that you normally see, fluorescent light, everything that occur in this way. But this also opens up a route to a new type of light. It's called laser, where, for example, some of these higher energy levels could have much longer lifetime. For example, they could store up a lot more electrons in that higher energy state for a long period, and then they could all de-excite all in one go. So when they do that, this produces a very strong flash of light, very strong emission of light, a collection of photons all in one go. So it's unlike the normal light that we see, where there's no real control on at what time different photons come through. It's like a crowd. It comes essentially through spontaneous emission, which, if you really go into quantum field theory and things like that, you'll say it's because of vacuum energy fluctuations. So we don't need to go into any of those things for now. All you need to understand is that there are ways to de-excite atoms or all the electrons in higher energy level all in one go, and that actually produces a very novel type of light source called laser, where all the photons actually emit at one constant period of your choice. So this is actually very useful, and if you were to create a pulse, for example, one of the prerequisites is that when we mentioned flashes, one of the prerequisites is that the flash has enough light, right? It needs to have enough photons to, in a very short period, to scatter off from an object, so that you can it comes back to your eye or the film, so that you can actually capture that fast motion. So in order to supply that many photons during that fast motion is actually quite challenging. So if you were to create a a pulse, a short pulse of light, chances are that you may want to do this using a laser, because there you have control on when you emit all the photons, and they all emit in one go, so you can in principle get much brighter pulses or much shorter pulses using lasers from that way. Now, before we get into producing a pulse, it'll be good to look at, maybe you have learned this in electronics, something called Fourier theorem. So essentially it has two concepts. You'll see this in light also. You may have come across this phenomenon called interference, when you have a wave that has a certain wavelength or frequency. So I will, in this talk, I will switch between the concept of wavelength and frequencies. Essentially, how many times a wave repeats itself is essentially the frequency. Is 1 over wavelength, 1 over lambda is a frequency. But it also has a phase, so that when the peaks of the wave, or as we saw in light, is an electromagnetic wave, so the peaks of electric and magnetic fields, when they completely overlap, so they can actually, we can say it is in phase, they add up, they create a constructive interference. But when they are out of phase, let's say 90 degrees out of phase, they can actually completely cancel each other. So this concept of phase, adding things, and constructive and destructive interference is important for understanding how to create Attoseconds pulses. I just want to introduce that concept here. The other concept I want to introduce is, which is actually a very useful concept that is used even now to produce fast electronics and things like fast, wave generators and oscilloscopes, something like that. This concept is that you can generate any shape of waveform by adding sine waves, which are essentially the simplest plane waves that you can imagine. By adding different sine waves of different amplitudes and different phases, you can actually create any waveform. So this is actually important, and this is actually one of the fundamental principles of how you generate light pulses, or any pulses for that matter. So if you take one step forward from that concept, you can see that to create a very long pulse, if you go back to create a very long pulse, you don't need so many waveforms, so many sinusoidal waves. If you look at the spectrum, or the different wavelength components that you need, or the bandwidth that you need, you don't need much to create a long pulse. But if you, on the other hand, want to create a very short pulse, something like a very sharp edge, like here, it is very likely that you need to add up a lot of sine waves with different frequencies or different wavelengths. That means that the bandwidth, or the range of frequency that's required, is much larger. So this comes from a signal theory perspective, but this has relevance in quantum mechanics as well. So if you've learned quantum mechanics, at least in your later BSc days, you may have come across the Heisenberg uncertain principle, where it actually starts with position and momentum, which you can actually convert into time and frequency domain kind of relationship. So which means that in order to have very short pulses, so delta tau, very small, which means that you need 1 over delta nu. Delta nu is basically the bandwidth. So it's inversely proportional. So to get really short pulses, for example, femtosecond pulses. Femtosecond is 10 to the minus 15th of a pulse, so a million billionth of a second. You need a lot of bandwidth, and to get attosecond pulses, which is 1,000 times shorter, you need even higher bandwidth. So this essentially is the challenge that we're going to deal with, how to get this kind of bandwidth and how to add them up. This essentially is the rest of the talk. So to do that, first of all, you need to understand how to produce light pulses first using lasers. So as we saw earlier, depending on how short the pulse is, the frequency components or the colors, different colors or bandwidth that is required to produce that pulse varies. So for long pulse, it's very easy to get material that will actually support such pulses. One such material is actually there. I don't know if you can see it, showing into the camera. So this is a rod. It's a glass rod doped with neodymium, and that's what gives it that pink color. Okay, so this can support some bandwidth, but not enough bandwidth to get very short pulses. But there are certain other materials like sapphire doped with titanium that can actually get 100 terahertz, which is 10 to the 14 hertz. It's very close to 10 to the 15 that we said. So this can support tens of femtosecond pulses. So this is essentially the material. This titanium doped sapphire essentially is a material that people use to produce very short pulses, especially femtosecond pulses. So you need these pulses to create even shorter pulses. This is why I'm mentioning this. Now, just by having that material and having a lot of color or a lot of bandwidth doesn't necessarily produce a short pulse on its own. So for a laser, what you typically do is you have a cavity, you keep the laser material, in this case, let's say titanium sapphire in there. It can support a lot of bandwidth, as we saw. And within the cavity, like you would have seen in your +2 lab, you may have seen this resonance column experiment, right? So by changing the length of the column, the frequency that the column resonates changes. Basically, each cavity can support only certain modes. So similar to that, even a laser cavity can support only certain modes. So these frequency components that are actually supported in the bandwidth can, as we saw earlier, can add up, can start interfere. And they will constructively interfere only when these different wavelength components are in phase. But if they are phased randomly, if they are oscillating randomly, you will not get a pulse. So they have to be locked together in phase. So there's a technique called mode locking that actually enabled these different wavelength components to lock together. And this is basically the technology that enabled short pulses. That kind of led to pretty much everything that we're going to discuss later on in the talk. Unfortunately, this technique never really got Nobel Prize, but the science that people use, people like Sivale, use these femtosecond pulses to understand chemistry, that got Nobel Prize, but not the technique to produce short pulses, unfortunately. So we saw that we can actually get femtosecond pulses, but can you go shorter? I mean, our ultimate aim is to get to attosecond pulses, and this is where you come to the fundamental limit of what actually light means. So as I said earlier, so light essentially is an electromagnetic wave, which means that you have oscillating electric and magnetic fields. So you need to have at least one cycle for you to have to call it a proper light. Otherwise, this can't propagate through vacuum. So you need to have at least one oscillation period of electric and magnetic fields for it to be able to call it a light, and that depends on the frequency of the, how short that time period is, depends on the color, depends on the frequency of the light. So most of the lasers that were used to produce femtosecond pulses earlier were actually in this regime, around 800 infrared. So they can produce a few femtosecond pulses, but to get to attosecond time scale, you had to go much shorter wavelengths. This is the problem. So for infrared, let's say if you take 800 nanometer light, the one cycle period is about 3 femtoseconds, 2.6 femtoseconds. But so using a infrared laser, you can never get to an attosecond. But you can do something clever to get shorter wavelength. One such way to get shorter wavelength is producing overtones of these frequencies. So like, for example, you may have heard this if you are musically bent, if you have a veena or guitar, pretty much any string instrument, when you pluck it, they can support certain it's essentially like, you can imagine you have two ends. That cavity can support multiple frequencies as long as the notes are at the end. So these are different overtones that this can a string can support, or string instrument can support. So, but when you come to optics, we call them harmonics. So how are they generated? So you don't normally see them in normal life. This because the light that we normally see it's not really intense enough to produce harmonics. So light we normally see, like sunlight and our incandescent light that we have in our houses. So the way they interact with atoms, essentially, you produce a dipole in an atom. If you just consider an atom in any material, when light interacts with it, basically produces a dipole just by moving the electrons or electron cloud slightly away from the nucleus, and that sets up dipole. And it's essentially this oscillation of this dipole that actually defines the entire interaction of light with matter. It defines the refractive index. It defines what color it emits. So when this when light at certain frequency, as I said, it oscillates. This electron cloud also oscillates pretty much in the same frequency. So you can actually see the polarization, which is kind of the quantification of how much electron cloud displacement you have had, is proportional to the electric field. It's linearly proportional. So it basically just oscillates the same frequency, which is why when you shine a light of certain color, everything appears in the same color. So there's nothing nonlinear. But if you go to pulse lasers, for example, pulse lasers can have much higher power. So basically, because pulse lasers emit all the light in a very short time scale, the power can be actually quite large. So when you say power, unit power in power in unit area will be intensity, and the electric field essentially is the square root of intensity. So you can actually reach much higher electric field or much high intensities using pulse lasers. This is again another fundamental principle that you need to understand in order to get into nonlinear optics. When you have such strong light interacting with matter, this motion is no longer linear. It's no longer it's no longer simple harmonic motion. So you can actually have a harmonic motion, pretty much like a weight hung on a spring. You can actually write the displacement and equate that to force. If it is simple harmonic motion, you basically have a spring constant comes in, but it's a linear relationship. But if it is anharmonic, you can actually see multiple powers of displacement coming into picture, right? So similarly, if this motion is nonlinear, if the motion of this electron cloud is violent, you actually can get much higher. It'll be it'll be responsive to much higher powers of electric field, not just the electric field itself. So this is where the nonlinearity comes in. And when you convert that into, you put in, as I said, electric field is e power I omega t. This is where that concept of mathematics comes in. When you put that in, you basically get almost like a Taylor series. And this is where the multiple harmonics or multiples of the fundamental frequency comes in. You start getting 2 omega, 3 omega, and things like that. And then you start getting, if you shine one light into some nonlinear material at high intensity, you start getting different colors than what you put in. But even this kind of conventional nonlinear optics is actually not sufficient to get to attoseconds. So typically with nonlinear optics, you can get to something like 200 nanometer, maybe 150 nanometers. Below that is actually quite difficult, partly because most materials don't really support it. Matching the phase becomes very difficult. So you kind of need a different process to really get into attosecond regime. So at this point, you don't need just a harmonic generation, you need a high harmonic generation. And it's not enough to just violently shake the electron cloud. You need to actually start breaking the electron apart from the atom, and which means that you need much higher intensity. You need much more intense pulses. And to generate these intense pulses, you need a different type of technique called chirp pulsed amplification. Essentially, it starts with a very short pulse, and any pulse, as I said, has multiple colors. So you don't want to really amplify these pulses in order to just get high intensity. You can't do that in one go because it will start damaging a lot of optics on the way. So what people do is to stretch this pulse in time by splitting different frequency components or different colors in the pulse into a spatial domain and move them apart spatially. So you can make the red part of the pulse travel more compared to the blue part, or vice versa, which means that you're stretching this pulse in time. It's called chirping. Then you can amplify. The pulse is long, so you can start amplifying it. The power will not be strong, which means that you're not going to damage anything on the way. And once it's got enough energy, you can reverse this process. So if red travel longer period, longer distance, you can make the red travel lesser distance now, and vice versa. So people use typically prisms or gratings for this phenomenon in order to split light into different colors and then combine them and make different light components travel different ways. So this technique was essentially invented by Gerard Mourou and Donna Strickland, and for that they actually got the Nobel Prize a few years ago, back in 2018. So this technique called chirp pulse amplification was essentially required to produce attosecond pulses in some ways. So this enabled the most intense lasers possible. So some of the lasers that we have, in fact, 2 lasers that we have, are the most powerful lasers in the world. So you can actually create extremely large intensities using these, as much as if you imagine a lens as big as Earth, and if you focus all the sunlight that is falling on Earth onto a tip of pin, you can actually create that kind of intensity using these lasers. And pretty much anything that you put at the focus turns into plasma. It pretty much becomes like centers of stars, like sun. So this is an entirely new field, entirely different talk altogether. But I'm not going to get into that now. But essentially, I'm just saying that this technique has a lot of applications. But essentially, the same physics that we use for generating attosecond pulses. But for this, you don't need such high intensities. You need intensity, but you don't need very.
Sorry to interrupt you, Rajeev. I have a quick question out of curiosity. So you said that we need to especially separate the different components.
Yes.
So what could be the typical space?
So Yeah, so it depends on what the beam size is. So and depends on how much you want to stretch the pulse to. So typically for a high power laser, you start with a very short pulse, femtosecond pulse, and before you amplify it, you may want to stretch it to maybe a nanosecond or so. Yeah. So to do that, it'll typically take a meter or less than a meter if the beam size is, if the beam diameter is small, and then you start amplifying it. But as you start amplifying it, the energy is more, obviously, so the power also goes up. Even though the pulse is long, the power is still high. So you want to start expanding the beam to much bigger beam diameters. So some of these high power lasers, the beam diameter is not this much; they are actually this much. So there are meter diameter lasers available. So when you have such beams, and then you want to reverse this spatial chirping that you did, then you had to space these gratings much further. So some of these will be several meters apart.
Thank you. Thank you.
Okay. So just moving on. So again, as I said, you don't need that kind of really high intensity to produce high harmonics. All you need to do is to be able to ionize the atom, just to release the electron. So just to look at one electron, simplest thing, hydrogen atom. Again, the Coulombic field that is binding the electron onto the nucleus is about 10 to the 9 volts per centimeter, which can convert into intensity. In some ways, it will become 10 to the 16 watts per centimeter square. It's a very funny unit. It's not SI, it's not CGS. It's a combined unit in some ways, purely because of historical reasons. So, but you don't even need that kind of high intensity for ionizing most atoms. I'll come to that why in a second. Typically, to produce high harmonics, you only need about 10 to the 14 to 10 to the 15, an order of magnitude smaller intensity. So all you need to be able to do is to just ionize it. And how that is happening will be clear in the next slide. So before we go to the next few slides, so I'll probably take another 15 minutes or so, if that's okay.
Yeah, that's
get to fine. Yeah. As I said, I need to stop at 11:30 UK time, but we still have about 35 minutes for that, so we have plenty of time. So I think it'll be important for you to understand some of these quantum mechanical concepts. It'll be trivial for some of you, but it will not be trivial for some others. Is that just like light, as I said, you have wave and particle nature. Same for pretty much any matter. Any matter has any particle. Any matter in general terms has a wave nature as well, and this was proposed by De Broglie, and this has actually been experimentally proven. And this interference pattern that you see here is not obtained by light; it's actually obtained by electrons going through two slits. So the classic double slit experiment, it was done by using electrons, and they actually produce interference pattern. So we know that any particles have also a wave nature, which is good. But then the next step is that when they are confined, or when they are confined in a space, for example, in a potential well of let's say an atom, which is where electrons are kind of bound by the Coulombic potential, then the space or the position of the electrons is actually somewhat fixed, which means that their momentum, because of the uncertainty principle, becomes completely undefined, which means that you need, in a frequency domain, you can see that you need multiple waves to actually define the wave function of a bound electron, which we typically call wave packet. So the wave packet is, this concept wave packet is actually central to understanding Attoseconds science. Now, when you have a wave, a particle wave, confined or stopped by a potential or a barrier, something interesting happens. So in classical regime, the only way for a particle to actually cross that barrier is to basically get more energy and climb that barrier up and go down. But in quantum physics, because this is a wave function. Wave function means that it's an addition of multiple probabilities, which means that there is a finite probability for the wave to tunnel through without actually going over the barrier, which means that if the barrier is sufficiently low, it comes to a point where the wave function of electron can actually tunnel through the barrier and actually ionize. So this is an important principle. It's an important phenomenon that actually happens prior to producing high harmonic generation. So it's pretty much now everything is there to produce our first high harmonics, and you have the short pulses, you have the intensity, and you know how tunneling works, and this is basically what Lullier did back in late 80s, 87 actually. So she produced the first high harmonic spectrum, and this was the paper that she reported this thing. Basically, you start with a laser, you have a gas jet, intensity is not very high, and you basically have a spectrometer with gratings, and you basically look at the different wavelength components coming out of it. And just to understand, just looking at my calendar to see when should I go. I should be okay, I think. Yep, I have some more time. Yeah, that's fine. So if you look at the wavelength components that she saw, it's actually quite interesting. This is basically the high harmonic spectrum that she got. So you have harmonics of the fundamental frequency, odd harmonics. I'm not going to get into why only odd, but maybe later on in the question section. So you have a drop, which is what you would expect as you go higher and higher harmonics. If you go back to the nonlinear optics analogy in perturbability theory, this is what you would expect. But then, interestingly, there's a plateau, and then there's a cutoff, and people didn't really understand why. Although it produces high harmonic spectrum with enough bandwidth and everything, didn't understand how this was produced until Paul Corkum came along with a very simple model to actually explain this. So the explanation was that, imagine an atom, you have the electron stuck, bound by the atomic potential, or in the quantum picture, a wave packet, and during one half cycle of the light field, the electric field will follow in one direction. It can lower the atomic potential in one way, so much so that the electron can actually tunnel through, and this electron can actually almost get out of the atom, and by that time the field gets reversed, because it's an oscillating field, and when it reverses, the electron will actually start, it'll act on the electron, right? So it'll start going back to the atom, and it'll start accelerating in the electric field, and when it actually recollides with the parent ion, it actually emits the high harmonic. So this three-step model, where the atom ionizes, gets accelerated in the electric field, and then goes back into the atom and collides it, producing this high harmonics in XUV, X-ray ultraviolet regime. That was actually critical in understanding how this whole phenomenon actually works, and to actually understand how this could, in principle, produce attosecond pulses. So this actually is from his paper. So he basically looked at what happens to the electron in the electric field. I'm not going to get into this. Basically, you can actually write the equation of motion. It's completely Newtonian. You can write the equation of motion for the electron in the electric field. It gains energy, a certain energy, what we call quantum motive energy, and depending on the key insight that in that paper was that, depending on the time of birth of the electron, depending on at what point of the cycle the electron got born, the energy that the electron gets will be different. So, and Paul argued that the maximum that you can get will be in the quarter of the cycle, at 17 degrees and 197 degrees. Basically, if you assume one cycle at 360 degrees, you can see 17 as just at the just before the peak, and the 197 is just before the peak of the other pulse, other cycle, and that's when you get maximum energy harmonics, and this could actually explain the entire high harmonic spectrum. So this was the key idea that Paul Corkum brought in to actually understand. Now, because the electron is actually born not during the entire cycle, but at certain parts of the sub-cycle, this naturally becomes an attosecond phenomenon. So this is where the first attosecond glimpse comes in. So just to show it pictorially, so you have the atom, you have the electron that is released by the light field. It kind of recollides it twice during one cycle, one half of the cycle, and when the cycle reverses a second time. So you get essentially two harmonics, two XUV pulses per light driving light cycle. So this is actually important to understand how this could actually be an attosecond phenomenon. But the question is, using a typical laser pulse, is it possible to produce attosecond pulses just by producing harmonics? And as it turns out, not necessarily, because this is where the phase, if you go back to the phase discussion that we had, how different wavelength components needs to add up in phase in order to produce short pulse. Going back to how we produce femtosecond pulses, that same physics applies here. So if the phases of different harmonics are actually random, which could in principle be possible when you have a lot of cycles like this, what you get actually will be just rubbish. You may not actually get a very constant intensity attosecond pulses. You'll have a very random fluctuation of attosecond pulses. One way to make sure that you have these things add up in phase, you should reduce the number of light cycles. So you basically, instead of having a very long pulse, like let's say 100 femtoseconds or so, you go to a short pulse. You go to maybe few cycle pulse, let's say 10 femtosecond that has only 3 light cycles if you are in infrared, or 5 femtosecond, which typically will have only 1 full cycle in infrared. And that is one way to actually get to make sure these harmonics will add up in phase. But even then, it becomes slightly complex. So, for example, if you have a lot of cycle, then this is showing the pulse envelope and different cycles within the pulse. But if you reduce that to few cycles, then it really depends on where the electric field of the pulse or electric field of the light wave actually peaks, right? Because this is essentially the carrier envelope, carrier frequency, but this is the underlying cycle frequency of the driving field, and you can see why the phase becomes important. So if it is slightly out of phase, it could be that the peak of the electric field may not be actually at the peak of the pulse, which means that it will be completely out of phase. So when you produce harmonics, where the electric field of the individual light cycles actually peak becomes very important. Otherwise, you may not actually get a proper harmonics. And as just illustrated in some other way. So as we said, every half cycle produces say XUV pulse in a multi-cycle pulse. You'll get a spectrum like this per pulse. But if you go to very short pulses, like few cycle pulses, in principle, you can get an isolated attosecond pulse like this if the peak of the pulse is coinciding with the carrier frequency, or if it is slightly off-centered, then you will not get a single attosecond pulse. You can actually get you can actually split them into two. So it was actually important to get to a technology that will actually allow you to create phase stabilized lasers as well. So this was actually developed in parallel in late 1990s.
Sorry, Rajeev. Sorry. Yeah. If you could finish in 5 minutes.
Yeah, I will finish in 5 minutes. Yeah. So this was important to actually produce attosecond pulses. This idea of I have only, I think, 5 more slides really. So to get attosecond pulses, this was actually important. So now you got all the scenes set for this high harmonic pulses from each half cycle to add up coherently and in phase, producing short attosecond pulses. So in principle, with short few cycle pulses producing high harmonic generation, you now have produced attosecond pulses. However, to really know that they are attosecond pulses, you need to actually be able to measure them, and this is the problem. So when you have a very short pulse, when you produce something that is much shorter than whatever you have done before, how to measure that? In order to measure that, you need to have even shorter thing, right? Because in the same analogy as a shutter speed, we use minute handle to understand hour. We use second handle to understand a minute. So same way, don't you need something even shorter, maybe a zettosecond, to actually measure attosecond? As it turns out, you don't need to. So this is actually done in measuring short pulses. There's a technique called autocorrelation, where you actually use the pulse itself to measure it. So you basically cross two pulses like this into a nonlinear medium, and you basically look for a signal where that is corresponding to nonlinear overlap of these two pulses. And when you look at the signal, how that varies by changing the delay between these two pulses, you can actually measure the shape of that pulse. And this is kind of a standard procedure that is done in short pulses. So what Agostini did, sorry, there is a fire alarm test here. It'll just go back in a couple of seconds. Right. So what Agostini did was actually to use the same principle, but instead use photoelectrons. Basically, they took high harmonic as well as the driving field, focused both of them onto a gas jet to produce electrons. XUV pulses, these harmonics, they produce photoelectrons when they ionize gas molecules, and the IR field also will produce electrons, and they appear as side bands in the photoelectron spectrum. And by changing the delay between these two pulses, the XUV and the driving pulse, you can actually measure the shape or the duration of the attosecond pulse. And this was done for an attosecond pulse train in 2001, and they measured something like 250 attoseconds. This is the first time someone actually measured an attosecond pulse. So just 2 more slides. So in order to do, what if you have a single attosecond pulse? So you have another technique, again used in measuring pulses. It's called a streak camera. So where, for example, you have an incident light pulse that produces some photoelectrons, and what you normally have is a voltage plate where you streak. We basically have a voltage that changes with time. You increase the voltage in time, and that voltage acts on these electrons and basically sweeps them across. It basically maps different velocity of the electrons into different space. So you can actually imprint a spatial image of a temporal temporally dispersed electron pulse in space in history camera. So what KAAS did was to actually use the light field or the driving infrared light field itself to streak the XUV generated photons. So what he did was something similar. So you took the high harmonic pulses, made an isolated attosecond. I'll come to that in the next slide. Produced photoelectrons and swept the laser electric field across it to measure the energy or the momentum of the photoelectrons in order to actually map the shape of that XUV pulse, in which case this was attosecond pulse. Just to show it pictorially how they sweep it, you basically have this XUV pulse that is coming in, which produces photoelectrons from the gas jet, and you basically sweep the infrared light field across it to look at the energy, and then you get this famous picture where a single attosecond pulse was imaged for the first time, so this was again published in Nature in 2001. So for these two, this is going back to what I said earlier, for the experimental demonstration of attosecond pulses. This is why Lullier, Agostini, and KAAS got Nobel Prize for. So where the field is going, so you, for example, this has a lot of applications. Now you are really getting into the inner works of atoms. You can actually start understanding how electrons actually behave inside atoms, even in inner shells. And just by doing that, you are actually confining even not just the temporal scale, but also the spatial scale into angstroms. So you can actually have, in principle, attosecond angstrom level imaging of things that's never been possible. So this field obviously has a lot of applications in a variety of fields. For example, you can understand how molecule or the molecular chemistry inside, before even bond happens, actually occur. Things that we thought are instantaneous, for example, things like this photoelectric effect is considered to be instantaneous, but it actually is not. You can actually understand the timescales of these things, which will, in principle, make us improve things like solar panels and things like that, and even get to much faster electronics, because of the bandwidth that is available. You can image orbitals. This is an image of a molecular orbital, and these things were actually done only through quantum mechanical calculations so far. But now you can actually image them using just by looking at high harmonic spectra. Purely using them as a light source, you can also use techniques like tachography, for example, to beat diffraction limit of imaging. So this is an image of a mouse neuron that is only tens of nanometers long. So it's a good source, even as an imaging source, for example. So when asked and about applications in the Nobel lecture, Anne Lullier was saying we are only about to scratch the surface of applications of attosecond science. So I think the future is, pun intended, bright for attosecond science. So this is where I stop. So thank you.
Yeah, thank you very much for this captivating and engrossing talk. Right. So there was a nice flow. I mean, starting from what it takes from the college level all the way up to producing the femtosecond pulses. Before taking too much time, I will check with the audience if there are any questions from them. I have a couple of questions, but maybe
sure.
Yeah, Sushil is there. Sushil is there. Yeah. Yeah, Sushil, you can unmute yourself, and then you are on mute, I guess.
Hi, Rajeev.
Hi.
So nice to see you after a long time. So very interesting, very fundamental, and very for general public I appreciate this talk. And just because I worked in high intensity, I work now working at long pulse lasers at Pulse Laboratory in Prague. So And also I work in laboratory plasma, tokamak plasma. So I have different experience from IPR to ELI beamline to pulse laboratory and all that. But I never work in attosecond, for example. 10 power minus is very narrow pulse, very small pulse. But only question is that what is the uncertainty measurement, like what is the uncertainty in the measurement of these attosecond pulses? What we see in the theory, and when we measure in the experiments, how much uncertainty is there? Like for example, 10%, 20%, or 30%? Just for my curiosity, because I never worked in that field.
Yeah. So some of them are actually surprisingly accurate, and the main uncertainty in these things actually come from the quantum mechanical uncertainties themselves.
Yes.
Because, for example, when I showed that image of this molecular orbital, there were even questions whether they are actually right, because the orbitals actually change time. It's only a snapshot of such a thing, right? Because it's only an interpretation in some way. So most of the uncertainty of this attosecond measurements actually come from the fundamental Heisenberg
principle. Yeah.
Uncertainty. Obviously, there are uncertainties that happen in the measurement, for example, but these are experimental uncertainties. For example, how it's not a theoretical uncertainty, as in how accurately can you measure?
It's diagnostic capability, basically.
Yeah,
diagnostic capability.
No, so how accurately can you measure energies of certain thing? If you're looking at photoelectron spectroscopy, for example, people use things like Coltrane, something like this. What is the resolution of that? Those things actually transpose onto these things, but fundamentally, the fundamental uncertainty will still go back to the quantum mechanics.
And just relevant question is like how, like nowadays everywhere is ICF fusion, blah blah blah. So how these kind of attosecond pulses can be helpful to measure some things from the fusion point of view, some radiations or some kind of information which is happening inside the plasma, particularly laser plasma interaction with very high power lasers, you know.
Yeah, so that's an important question. So now the fusion mostly deals with things that happen within nucleus, which actually has much shorter transition periods, as you know. But if you are using certain types of particles to induce fusion, for example, in order to optimize some of those emissions, if you for example want to control those emissions by, let's say, dicing up some certain stages, those things actually can in principle be done with this attosecond control. So it's almost like when femtosecond lasers became fashion in 2000s, there used to be a field called coherent control. So it started with Ahmed-Zivel. It kind of transcended that field. You could control chemistry in some way, but using attoseconds now you can actually control the thing that happens before the chemistry.
Exactly,
so even transitions, atomic transitions can be in principle controlled. So from that perspective, it may have an application in fusion, but probably not directly, not in the nuclear transitions.
Mm-hmm. Yeah, thank you very much. Thank you.
Yeah, thanks, Sushil. Vishal, yes, you can unmute yourself and ask the question.
Thank you for a very fundamental talk. I just want to ask, in one slide, you have shown the wavelength of 800 nanometer, which is falling on the X-ray spectrometer, and you are measuring that on the CCD detector, I guess, a detector. I just want to know if you are using a visible light, and how do you measure using the X-ray spectrometer, and what kind of detector are you using?
Let me see which one it is. Okay. Yeah, I think I know which slide it is. This slide, right?
We cannot show your screen.
Yeah, you have stopped share. Yeah, it is coming up.
Yeah, this slide.
Yeah, okay. So no, so they are not actually measuring the visible light. They are actually, or the infrared light in this case. What they're doing is, so this is essentially the simplest setup for high harmonic generation. So you start with a short pulse laser, you focus it onto a gas jet, and from the physics that we went through, it produces high harmonics, which is actually an XUV regime, and then you basically pass through an X-ray spectrometer, it is actually the way X-ray spectrometers are done. You basically have a crystal that are at grazing incidence, so they could. The fundamental part of it is essentially it's not diffractive for laser wavelength, but it's diffractive only for the X-ray wavelength. Yeah. So for light wavelength, it'll just be reflective. It'll actually come through, but it will not go to the detector itself. It'll actually go to a dump.
Right. So, are there any other questions? Because I can see there are only 6 minutes to 11:30. Okay. So Prashant, yes, please go ahead.
Hi, Rajeev.
Hi.
Good talk. Yeah. So just one, on the high end side, the solid harmonics. What happened to those campaigns?
Yeah. So this is an interesting thing. So solid campaigns are actually ongoing. So solid harmonics, by the way, you do get odd and even because of symmetry breaking, and the conversion efficiency is actually higher as well. So so a lot of people actually started looking at solid base harmonics with the only downside is that you need much higher intensity, to have this. So so people started looking at this a few years ago. The problem was that to enable